Sorry about the kind of small print here, but we have a clinical trial that was conducted to test the effectiveness of a drug used for treating insomnia. After treatment of the drugs, 23 subjects, so I'm just going to write n equals 23. We had a mean wake time, so their sample mean was 98.5, and we had a standard deviation, so it comes from a sample, so I'm going to write S instead of sigma. Standard deviation is 43.5. And then we're assuming that it comes from a normally distributed population, and we're supposed to construct a 95% confidence interval. So with whatever test statistic we're about to get, when they say 95% confidence, remember if you use a table, you're going to be looking up 0.025, or in other words 2.5% for one of the tails, because 95% confidence means 5% is left over for two tails, because our confidence interval is centered. Okay, 95% confidence interval for the standard deviation. And that's not a question that comes up a lot. We're asked to make a confidence interval for the standard deviation, not for the mean. Okay? And so I pulled up the formula for a confidence interval for a standard deviation. It comes, I think I got this straight from the text. Oh, it's gone now. What did I do? I think it just disappears underneath that picture. Okay, comes from the text. Look, the mean isn't involved. X bar isn't anywhere in the formula. So this question's kind of tough because it's got some information that we actually don't need, and I think that throws students off. If you need a confidence interval for the standard deviation, for the population standard deviation, you just need the sample standard deviation. And then you need a test statistic called chi-squared. If you look in the back of the text, it's a table that works really similarly to the t-table that you used before, and which is kind of similar to the z-table. It's just a different table that we have to use. I'm going to use online software to do it because I think that's a little quicker. But so we have n for the formula. We have s. We need chi-squared. So I'm going to go to Google. I'm going to search percentile to chi-square calculator. Like if you needed a t-value for like a 95% confidence interval, you could type in t-score to percentile calculator. Okay. Let's just use the first one that comes up. And so this is the red area is what I'm about to type in here. We're going to type in 0.025 for the reasons we said before. And now the degrees of freedom, it's for one standard deviation here, it's n minus 1. Okay, so 23 is my n. That means my degrees of freedom is 23 minus 1. I'm going to punch in 22 here. And then hit execute. And where is it? So we got 10.982 for one of them. 10.982. And then we also need the upper tail for 0.025. That means that there is 0.975 to the left of this alpha over here. Right? I shouldn't say alpha because alpha is both of these. But so everything to the left of this upper cutoff for a confidence interval, that's 0.975 of the area. So here we're going to type in 0.975. Or I think you could have just clicked upper Q right there, and that would have done the same thing. We got 36.781 if I round. Okay, and so the way you're going to know which one's which one's x, which one's not x, sorry, which one's chi-squared sub r or chi-squared sub l is the left-tailed area is supposed to be less. So whatever calculator you're using, you know that the left tail area is supposed to have a smaller chi-square than the right tail area. Just like with z and t, the further on you go, like the further to the right you go, the larger your critical value or your test value or z-score value, all those things should be. The further to the right on the number line, the bigger the number. Okay, and you will see that if you were to switch the order, that's the only way the formula would make sense, because then you would get a value that's bigger, less than a bigger value, a smaller value. But anyway, once you get those straightened out, make sure I said it again, make sure chi-squared sub r is bigger than chi-squared sub l. Then you can plug the values into the formula. So we got 23 minus 1 times our standard deviation squared. divide that by x sub r. It's going to be less than sigma, which is our population standard deviation that we're trying to estimate, which is less than or equal to we got 23 minus 1, 43.5 squared over x sub l squared. Oh, I moved it. It's 10.982. That just takes some work with a calculator to simplify. So if you're not comfortable with simplifying with a calculator, if you think maybe you're doing the order wrong, you'll want to do this step by step. But I'm going to do 43.5 squared, so I multiply by itself. Then I'm going to multiply that by the 22. And then we're going to divide it by the 36.781. And then if I hit square root, I've got the left side simplified. I've got 33.6, whoops, lost my calculator, 33.643. And then same thing over here. I'm going to do the squaring first because that's what comes first in the order of operations. And then multiply that to 22, then divide it by 10.982, and then apply the square root, 61.569. So there's our confidence interval. I think it said actually to the second decimal place. Yeah. So I'd say 33.64 for the left endpoint, and then 61.57 for the right endpoint over here. Does this result indicate whether the treatment is effective? So unless the treatment was supposed to like reduce variation, standard deviation only measures spread of data, right? It doesn't tell us whether one's better than the other. So yeah, I don't want to give away the answer because I think it's the same answer for everyone here in this next one. But you know, when you calculate a confidence interval for a mean, that can tell you whether you're having a statistically significant effect, whether you're changing things, whether you're making an improvement on previous medication. If you're calculating a confidence interval for a standard deviation, that's just telling you, a range of how much variability is in the data set. It doesn't necessarily tell you whether it's a particularly effective medicine. Again, unless the goal is to reduce the amount of variation in a patient's blood pressure. If that's your goal, then maybe the medicine's doing the right job.